let's see. So the topic of today's lecture is an attempt to do for PDEs and infinite dimensional systems in general what we've been able to accomplish for linear ordinary differential equations with state space in the LMI framework. So everyone off my screen so I have more space to work. So to get started, let's just warm up by reviewing what we know about state space for ordinary differential equations and linear matrix inequalities. So the state space formulation, coupled with the linear matrix inequality and semi-definite programming frameworks, has allowed us to solve most of the optimal control problems with respect to linear ordinary differential equations. And what has been the basis of this success is partly the representation of such systems, in particular, the 9 matrix representation, which has been developed for parameterizing such systems. So in particular, there's 9 matrices, which define the 9 maps from state, disturbance, and control input to derivative of the state, regulated output, and then sensed output, where the sensed output is then fed back into the control effort. So the ability to parameterize all such systems using 9 matrix parameters allows us to efficiently interface with software tools such as MATLAB and LMI solvers in a way which they can recognize and deal with efficiently. Coupled with that, we have this framework for optimization of positive matrices, which means that we can optimize and search over not just controller gains and system parameters, but positive Lyapunov functions, which have a one-to-one mapping between the positive matrices and the Lyapunov quadratic Lyapunov functions. Assisting us, of course, is not just the parameterization and the SDP framework, but the existence of efficient solvers, such most commonly being Sadoomi and Mosek, and significantly, but sometimes overlooked, the availability of efficient parsers to take sort of a high-level version of these optimization problems and convert them to machine intelligible formats in Sadoomi and Mosek. So with this framework, with the 9 matrix representation, with SDP solvers and efficient software tools, we can solve many of these optimal control and analysis problems. So for example, optimal estimation, optimal control, H infinity gain, and so forth. And the core of this is, of course, the use of Lyapunov functions to characterize these system properties. So in particular, there's a one-to-one mapping between positive matrices and positive Lyapunov functions. And moreover, if you take the derivative of these Lyapunov functions, the derivative itself a quadratic form parameterized by a matrix D, which then you make negative semi-definite. Coupled with that, we have strong duality results, which allow us to, coupled with a variable substitution trick, solve problems like H infinity optimal control. So as a result of this 9 matrix parameterization, the existence of efficient software tools for semi-definite programming in LMIs, we've solved most of these problems in linear ordinary differential equations. And of course, the question is whether we can do the same thing for partial differential equations. So let's introduce partial differential equations and give some introduction to our approach here to creating a state space representation of such systems. So the current formulation, I would say, of a partial differential equation is almost a historical accident. So partial differential equations such as the heat equation date back to the 18th century and came about at the same time as ordinary differential equations being proposed by both Newton and Leibniz. Who was first depends on whether you're English or French. But the heat equation itself, dates almost contemporaneously from the invention of ordinary differential equations. However, unlike ordinary differential equations, where the solution is uniquely determined by the initial state, partial differential equations had problems starting early on, in that they do not necessarily define a unique solution. There are many solutions to the heat equation. It wasn't actually until the 19th century when Dirichlet, this guy here, suggested that, well, if you want a unique solution to this PDE, you need to add some additional constraints to the solution to pick out the solution which is unique. And so he proposed adding a set of boundary conditions to the solution, which then, if the solution satisfies the boundary conditions and the PDE, then if there are a sufficient number of boundary conditions and they're suitably well posed, guarantees the existence of a unique solution for a given initial condition. Now, this was all very well and good until we got to the 20th century, when our notions of function spaces and notational systems improved, that Sergei Sobolev noted that, well, okay, just being a function isn't quite enough. This function actually needs to satisfy certain properties. In particular, of course, it needs to have that partial derivative exist. And of course, these limit values have to exist. And so he expanded this, the number of constraints on the solution to include a continuity constraint. So in particular, we have now, of course, Sobolev spaces, where not just the function has to be square integral, but the derivatives of the function have to be square integrable. And if they are, it's absolutely continuous, and hence these limit values exist, and of course, the partial derivatives exist. So as a consequence of this mathematical development over perhaps 300 years, we have that a partial differential equation at the current moment in time is not actually a singular form, but in fact defined by three sets of constraints, which implicitly, when intersected, define a solution. And one cannot ignore any of these when doing things like analysis and controls. And just to illustrate that, let's take the heat equation and consider an energy functional, or Lyapunov functional, which is just a square integral of the state here, just u squared integral, and take the derivative of it. And what we see when we take the derivative, of course, is one of these becomes a u dot and turns into USS. And so the problem here, of course, when we look at this derivative of the Lyapunov function, is it contains two terms, one u and one USS. And yes, there is some relationship between those two, but that relationship is nowhere encoded in the PDE itself. It's encoded somewhere at the intersection between the boundary conditions and this continuity constraint. And so you have to take an ad hoc approach to teasing out what the relationship is between U and USS in order to find some methods such as Poincaré's inequality, Werdinger's inequality, integration by parts, or what have you, in order to prove that this Lyapunov function is negative. So this is a very ad hoc approach and relies on the human to integrate these boundary conditions and continuity constraints. And of course, what we would like to do is find a way to do this automatically, teach a computer to do this without using ad hoc steps like Poincaré or integration by parts. So we've been looking at analysis of PDEs for quite some time. And we've always faced this question of what is the relationship between U and its partial derivatives. So at some point, we got tired of trying to deal with these things separately and asked the question, well, what exactly is the relationship between U and USS? And so we turn to something which is not conservative and is not necessarily ad hoc, which is just the fundamental theorem of calculus, right? Relating a function to its derivatives. And in particular, you can take a rule for repeated integration and get an explicit relationship between U, its partial derivatives, and these boundary conditions. So a singular form which takes into account these three things. And then, of course, if the boundary conditions are 0, right, then you have a direct relationship between these two numbers. And so what that allows you to do is go back to this heat equation, and instead of having an equation defined by both U and USS, well, what you can do is you can plug in your expression for U into this heat equation and get rid of U and have the entire equation expressed in terms of USS, so the second partial derivative. And so when you do that, you get an equation where you're not playing around with the right-hand side, you're instead playing around with the left-hand side. So now we have an expression for the left-hand side, which is defined not by partial differentiation, but by partial integration. So integration with respect to this spatial variable. So let's look at a slightly more complicated example, which is the wave equation, where again, we have another set of boundary conditions where now we come in on the right with one boundary condition on the left with the other. So now in a less systematic manner, you can also take the fundamental theorem of calculus and similarly write an expression for U in terms of the partial derivatives of U. So now here U0 and U1 come in, and we have to integrate from the left on first and integrate from the left and then integrate from the right in order to obtain this expression. But then once we do so, right, these things become 0, and we have a direct map between, right, the function and its partial derivatives, which we can now again plug back into the wave equation, eliminating U from the left-hand side, not the right-hand side, and we obtain a singular expression for the dynamics, not in terms of partial derivatives or any boundary values or continuity constraints, but explicitly in terms of a partial integration, first from 0 to S and then from S to 1. So this is what we typically think of as a partial integral equation. So it's defined exclusively in terms of USS. Its operators are partial integrals, which are bounded operators. And well, of course, there's a multiplier operator here implicitly, which is the identity. But the advantage of this, of course, is you don't need to account for anything like boundary conditions or continuity constraints, because there are no continuity constraints on USS. And given a USS, you can plug that back into this formula to obtain an expression for U. So that's the idea of how we can deal with PDEs without boundary conditions, or at least represent them, right? So now let's look at analysis problems like the Lyapunov function in particular. So let's look at a slightly more complicated Lyapunov function for the heat equation, where we've got the square integral of the state, but we also have these double integrals over here, and you'll just have to take my word that these are in fact positive. But given a Lyapunov function of this form, we can again, even this complicated expression, write it out as a quadratic form in U with an operator, which is a combination of a multiplier there, just identity, an integral from 0 to S, and an integral from S to 1. Okay, so now we can represent the dynamics and the Lyapunov function with operators of this form. Now, what about the derivative of the Lyapunov function? So what we do now is we take the same Lyapunov function and we differentiate it. So we get U dot appearing twice here. And then we do these substitutions first with the dynamics. U dot becomes USS on the right-hand side. And then we are left with something which is again a product of USS and U, which is unsatisfactory. So we'd like to eliminate U as well. And so we plug in now for U using this identity from the fundamental theorem of calculus. And we obtain an expression solely in terms of USS, where if we compose these two operators here, these two right here, we get another integral operator, which is again an integral from 0 to S and another integral from S to 1, where now this kernel here is a little bit more complicated, but it still has the same structure as the Lyapunov function and the set of dynamics. So the key takeaway is, of course, that the dynamics, the Lyapunov function, and its derivative can all be defined by the same class of operators. So let's take now these examples and try and make a framework which works for general classes of PDEs. So what are we going to need to do? We're going to need to define a class of operators which is going to take the place of matrices. So what are the key aspects of matrices that we use in analysis of ordinary differential equations, of course? The first one is that we can represent the dynamics using these matrices. The second is that we can define Lyapunov functions using these matrices, and we can constrained positivity of those Lyapunov functions. And then finally, when we take the derivative, the composition, addition, and transpose of matrices are also matrices, especially if they're square matrices. And so as a result, when we get the derivative, that's also defined by a matrix, which you need to be made negative semi-definite. So when we're constructing our algebra to replace the matrices, what we need in that algebra is A, the elements of the algebra can be used to represent a large class of PDE systems, linear PDEs, of course. They can be used to represent quality Lyapunov functions, that they form a star algebra, which basically means closed under composition, addition, and adjoint or transpose, if you want to make that transpose. They can't be finite dimensional, of course, because we're representing infinite dimensional systems. And finally, we need to have some efficient software tools available for optimization of parameterization of such operators. So that's our goal. And so now let's turn to a class of operators, which hopefully will allow us to meet these goals. So we're going to build up to it gradually, starting with just integral operators. So we denote integral operators with this little LK symbol right here, where we're talking about integration of the spatial variable. The input is u. We integrate out the spatial variable with a kernel. This is the kernel k. We integrate out theta, and then the kernel also has S in it, and we're integrating on the domain of the PDE here. So integral operators have lots of well-known and very nice properties, all proven sometime in the distant past, and all well understood. So in particular, the operator is Hilbert-Schmidt if and only if the k is square integrable, and we have an operator bound on the integral operator given by both the L2 norm and the infinity norm of the kernel. So, of course, when we talk about integral operators, we're thinking about them like operators, like matrices. And so it's this operator norm that we're going to be most concerned with. Next, of course, they do form a star algebra, but unfortunately, the problem is that there exists no identity operator. One of the problems, which there exists no identity operator. So it's not an ideal class of operators. We'll come back to that issue in a minute. So the first question we may ask if we want to parameterize integral operators is how to parameterize these kernel functions, right? Because we have no properties of the kernel functions other than square integrability and boundedness. The obvious solution is to use polynomials to parameterize these kernels. So polynomials are easy to parameterize using vectors and matrices. And so if we assume that k is a polynomial, then it's very easy to parameterize these matrices, these operators, and enforce positivity, as a matter of fact, but we won't get into that. The problem, unfortunately, if you try and parameterize integral operators using polynomials, is that polynomials are separable functions, which gives bad properties, if you will, to the operator. So in particular, all polynomials are separable. And what does it mean to be separable? That you probably already know means that you can separate the function into its two independent variables, where these are probably large vectors, right? So why is it a problem that polynomials are separable? Well, it's okay, and they do form an star algebra, so just like integral operators. But it's bad in that when you think about what these integral operators are actually doing, they're essentially projecting your input onto this finite dimensional space, and then those become the coefficients of the span of a new space defined by these functions fi. But because fi is a finite length vector, this is a finite dimensional operator, meaning that you can't do things like represent infinite dimensional systems like PDEs. Moreover, of course, you can't define positive Lyapunov functions if the operator is finite dimensional. And so polynomials are actually a very poor choice for parameterizing integral operators. So what's the alternative? Well, of course, multiplier operators work very well. We have lots of experience working with multiplier operators from transfer functions. And so, right, we use this little notation MF here to denote the multiplier operator associated with the multiplier F. So the input is U and the output is mu. Now, multiplier operators almost have an ideal set of properties, right? Their operator norm is precisely equal to the infinity norm of the multiplier. And they form a C-star algebra, which is even better than a star algebra in that it's closed, meaning that its square root and inverse naturally have the same structure as the original operator. Unfortunately, as we saw with the examples at the beginning of the talk, that PDEs cannot be parameterized using multiplier operators alone. This is not sufficiently rich structure of operators allowing us to represent these class of systems, which is probably obvious. So what's the alternative? We can, of course, I should mention, parameterize multipliers using polynomials. There's no problem with that. So the solution is to go back in time to the 1950s and use Goldberg's class of semi-separable kernels. So semi-separable kernels are, if you think of an integral operator as a matrix on infinite dimensional space, a matrix where the operator is defined separately above and below the diagonal. So you have different kernels above and below this diagonal, which corresponds to S equals theta. So obviously, if you just set K1 equal to 0 and K2 equal to 1, right, this is a full rank operator. So it's very easy to construct full rank operators using semi-separable kernels, even though the kernels themselves are separable. So if we can make these polynomials, right, we can parameterize semi-separable kernels. And although it says semi-separable, right, as opposed to separable, the properties of such operators are very, very different. So we can think of, for example, semi-separable integral operators as defined by the composition of a multiplier given by the first separable function, indefinite integration, and then another multiplier operator defined by the first function. So multiplier operators are full rank, and indefinite integration is also a full rank operation. And so we have the composition of 3 full rank operations, and that's another reason why semi-separable kernels are a good choice. They also, of course, form a star algebra, which is, of course, what we've been hinting we need for the whole talk. So semi-separable kernels, of course, not quite enough themselves because we do need those multiplier operators in there. And so we'll combine now this class of operators into a semi-separable integral operator and a multiplier operator. So this is what we propose as the what we call the partial integral algebra. It's defined by 3 parameters. That's why we call it 3π. 3 parameters: R0, R1, and R2. So 2 kernel functions, which we're going to take to be polynomial, and a multiplier, which is also going to be polynomial. This forms a star algebra, even if these things are polynomials. So in particular, it's easy to find these compositions, right? Composition, they just translate into a simple integration and multiplication of the corresponding parameters of the operators to obtain a new operator. Adjoint is even easier. It's just a matter of swapping variables and swapping functions. Okay. So given a semi-separable integral operator with multiplier, it's easy to calculate composition and adjoint. So are we done? Is that the algebra that we're working with? Well, not quite, because we're missing a class of infinite dimensional systems, which I didn't cover at the beginning, which is time delay systems. So time delay systems can be thought of as the coupling between an ODE and a very simple transport equation PDE. So where you have the ODE, the output of the ODE goes into a pipe at one end, that's this, flows through the pipe in time and comes out the other in its delayed format and goes back to the PDE or the ODE through this interconnection. So it goes back to the PDE, the ODE. So here we've got the interconnection of a finite dimensional system with an infinite dimensional system. We'd like to characterize this as well. So we just use the same trick as we did with the wave equation and the heat equation. We use the fundamental theorem of calculus to express phi in terms of phi s, and its boundary condition, which then becomes the output from the ordinary differential equation. We then, of course, substitute this expression into the dynamics, eliminating phi and expressing the whole thing in terms of phi s. And we obtain a partial integral equation here, where it's now the left-hand side is not just phi s, but it's also coupled with the ODE through this u dot term. And so when we express this thing, it's now not just a map from L2 to L2, but a map from R cross L2 to L2, R cross L2 to R cross L2. But the form has a similar structure defined by integral and multiplier operators on the left and the right-hand side. But we also have, of course, these cross terms, such as these integral operators. And so we need to expand our algebra a little bit to accommodate this new class of operators. So in particular, we propose this 4 pi class, 4 meaning both 4 parameters and 4 maps. So there's one map, which is a matrix, which is Rn to Rn, one map, which is an integral, which is L2 to Rn, one map, which is a multiplier, which is R to L2, and one map, which is L2 to L2, which is just a 3 pi operator itself and has 3 more parameters defined down here. So that's the dynamics of a time delay system, can be parameterized with 4 pi operators. What about Lyapunov functions and their derivatives? So, for example, for time delay systems, you may know that there are converse Lyapunov functions, which says that a Lyapunov function, quadratic Lyapunov function of this form is necessary and sufficient for stability. So this is the complete quadratic Lyapunov function. And it is precisely parameterized by operators of this form, with a matrix here, a integral here, a multiplier here, and of course a integral operator there. So now that we've defined this, and I should of course say that this also forms a star algebra. So now that we've defined this algebra, which we can use to represent systems and Lyapunov functions and their derivatives, the question we consider is how big a class of PDEs can be represented in this manner and analyzed in this manner. And so for this, we turn to representation of state space in terms of partial integral operators, which we call partial integral equations. And so the idea of this general conversion between PDE and pi is to take the PDE states given here, which are subject to what we sometimes call the domain of the generator, which is a combination of Sobolev space and boundary conditions, where this is just all possible boundary conditions on A and B. And we differentiate this state, stripping out the boundary conditions to obtain a state which doesn't need to lie in X, but only in R cross L2. So our pi state becomes our PDE state becomes this pi state, which presumably we would like to be able to convert back, of course, to the PDE state. So how do we convert back? That's actually the real question. What precisely is the relationship between these two states? So the first step is to generalize this rule for repeated integration. So generalize it in terms of these higher order derivatives and boundary conditions. And so it turns out that any function can be represented in any order derivative by a combination of an integral operator on that derivative, which is a 3 pi operator, and another, well, this is just a multiplier operator on this set of boundary conditions, which we call these core simple boundary conditions. So we have now an expression for xf and x in terms of 2 partial integral operators, but also these boundary conditions here, which you're going to have to do something about and get rid of. So the idea of what to do about these boundary conditions is to then just plug them back into this expression and obtain an expression for the boundary conditions themselves in terms of the fundamental state, or this pi state, these higher order derivatives, which will then set that itself be a 3 pi operator. And then we plug this back into the expression relating x and xf. And of course, the composition of pi operators and addition of pi operators is a pi operator because it's an algebra. And so we obtain then an expression between the pi state and the PDE state. So that's the idea in high level terms. And we can just see how this works with a second order general PDE, where now we have this all possible boundary conditions. So these are all the possible boundary conditions we have. So your boundary conditions in X are expressed in this form. Now we relate here through this Cauchy rule for repeated integration, X and XF, where we have a partial integral operator and then just a multiplier on these core boundary conditions. We then, of course, plug in for these core boundary conditions and obtain an expression for these all possible boundary conditions in terms of these core boundary conditions and an operator on the fundamental state. We then multiply by B, and because these satisfy the boundary conditions, that B thing here, this whole thing goes to 0. And now if BT here is invertible, we can obtain an expression for these boundary conditions in the fundamental theorem of calculus and substitute them in here and obtain a relationship explicitly between X and XF in terms of this fundamental mapping operator, which is of course a 3-pi operator. So what are the properties of this map between pi state and PDE state? Well, it's invertible, obviously, right? Because, right, if you have any PDE state, if you differentiate it, you get a pi state, and then you apply this fundamental mapping to that differentiated state, you get the original state back, right? So this operator is essentially the inversion of differentiation. This works the other way too. If you have a pi state and you apply the mapping, you get a state which is feasible for the PDE, and differentiation inverts that mapping, giving back the pi state. Most importantly, of course, however, is that this mapping preserves inner products. It's not only bijective, it's isometric. So that if you have the inner product of two L2, so two pi states, and you apply this mapping, the inner product in that new X space with the natural Sobolev norm inner product is preserved, right? So remember that the Sobolev inner product is the inner product of the partial derivatives. So this is a bijective isometric mapping, which in the same sense as the Laplace operator, we call unitary. And of course, this implies that this space, because L2 is a Hilbert space, this is also a Hilbert space. Okay. So armed with this, getting this mapping is the hard part. The rest is fairly straightforward. We take a general second order PDE. We plug in for TXF here and TXF here. And because, right, T maps this the X state to the X state, when you differentiate that state, this T operator with these partial derivatives here, you actually get back a 3-pi operator as well. That doesn't work in general, but because of how we define the map, it works here. So in the end, what we obtain is a unitary expression for the dynamics of a general class of, in this case, second order PDEs, but this of course extends to nth order PDEs as well, and two-dimensional PDEs as well, as Declan will probably testify. Now, I don't expect you to follow or even look at all of these formulas around here, just know that they exist. So what is the relationship between the pi and the PDE system? So we can characterize this in several ways. First of all, the solutions are equivalent. So in particular, if W and Z satisfy the PDE with PDE state X, then W and Z also satisfy the pi with pi state D alpha X. Second, if of course the converse direction, if W and Z satisfy the pi, then TXF satisfies the PDE again with W and Z. So as a consequence, the input-output properties of these two systems are identical. So in particular, L2 gain of these two systems is identical. Furthermore, stability properties are similar depending on which inner product space you use. So stability of the PDE with respect to the Sobolev norm is equivalent to stability of the pi with respect to the L2 norm. These are the natural norms for these systems. Of course, sometimes we use the L2 norm for the system, but so in that case, we have to say that that's equivalent to stability of this mapped state here, where now we've included the signal as well, because we have inputs. So now we have the algebra of partial integral operators. We've got the class of partial integral equations. The question is, what does this mean for questions of stability and analysis and control? So stability is easy, right? You just formulate a Lyapunov function of this form, take its derivative, and its derivative is defined by a partial integral operator because, of course, it's an algebra, it's closed under composition and adjoint and addition, right? And then if you can find such a positive operator and you can enforce negativity of the derivative, you have stability. All right, so that's straightforward. But we can actually say a whole lot more than that. Because of the algebraic structure of these operators, we get very strong duality results, right? Duality results which say that for every pi with inputs and outputs, there's an associated adjoint or dual pi obtained just by taking the adjoint of these operators and swapping, of course, B and C. Right? And remember, taking the adjoint is a simple matter of swapping variables in the operator kernels. The strength of this theorem says that these two systems have A, identical stability properties, ignoring inputs and outputs. And furthermore, they have identical L2 gain properties, so that the map from W to Z is, the norm of that is identical for both classes of systems. So armed with that, we can replicate many of the things that we did for optimal control of ODEs, such as the H-infinity optimal control problem. So we can formulate a dual version of the KYP lemma. This allows us to do that. And we can do a very little variable substitution trick where we take Z equals KP and then invert P to get back K. And as a result, we can obtain not just conditions for stability, but conditions for optimal control expressed as positivity of an operator, this is an indefinite operator, and negativity of a derivative form. So if you can find a positive P, such as this is negative, then the L2 gain of the closed loop system is bounded by gamma. So if you minimize gamma, you have a condition for optimal control. Now, I sort of brushed over the fact that sometimes we have inputs at the boundary, which cause this TU term, which doesn't appear here, to appear. And in that case, we have problems because it breaks our duality theorem somewhat. So if you think about what boundary input is doing, right, it's moving the end of this beam, if you want, it's a rigid beam or something like that, which if we think about continuity constraints, right, continuity constraints, the Sobolev space, implies that moving the boundary is not simply moving the edge and then all the other pieces follow. It actually moves every point in the domain instantaneously. So this is a bit of a problem from a mathematical standpoint because it actually means that the motion of every point is, of course, proportional to the rate of change of the boundary conditions. And so that's where you get that U dot term coming in. However, if you're okay with a little bit of conservatism, we can still get optimal controller synthesis conditions. So in particular, we can apply lots of these LMI techniques that people have used to develop LMIs, such as Young's inequality, allowing us to dilate the inequality and obtain sufficient conditions for optimal control. Well, then it's not optimal, but you get the idea. Now, whenever you see a big LMI, you can pretty much be assured it's a conservative condition. And this is no different, right? But in practice, what we find is that the conservatism is very small. And actually, you can get rid of the conservatism entirely just by filtering the input. So it's the state is affecting that, that boundary condition, not an input directly. So as a result of this sort of state space representation of infinite dimensional systems, we can take these LMIs, which have been generated for state space systems, ODEs, and move them over to the PDE framework with relatively little modification, just incorporating these T operators here from the left-hand side occasionally. And so we have conditions for optimal control, optimal estimation, H-infinity norm, KYP lemma, dual stability and stability. all that remains, of course, is a way to solve these things, right? We can formulate them as optimization problems, but can we actually solve them? Now that, of course, requires software. And so how do we solve these optimization problems? Well, there's two sort of basic questions we need to answer before we introduce software. The first is, how do we enforce positivity? Well, how do you enforce positivity operator in general? Well, in an algebra, or star algebra, we know that positivity is equivalent to the existence of a square root operator, right? So does there exist a square root, the square root test? So how do we test existence of a square root? Well, we have to assume that the square root has the same structure as the original operator. In particular, we assume it has a multiplier part, an upper integral, and a lower integral part. Or actually, that's reversed. And we parameterize such operators as polynomials with a matrix and a vector of basis functions. Those are the z things here. So that if the operator has in its square root of this form, we know, if this is defined as z here, that P equals Z star R transpose R Z. And now, instead of searching over matrices, which parameterize such operators, we'll take the square of the matrix to be a matrix, which is positive semi-definite. And we know that if Q is positive semi-definite, it has a square root, and hence the operator itself has a square root. So we'll convert operator positivity then to a question of existence of a square root defined by a positive matrix. And then the mapping between the matrix and the parameters of the square are given here. Now, inversion is the second question we need for controller synthesis. And again, we're going to turn back here to an old result from Goberg. There's ways to do this. There's an analytic formula for the case of separable kernels, but not semi-separable kernels because they're a little bit harder. In this case, we need to take these parameters and find their separable representation, because remember, we've assumed they're polynomials. This is easy to do. Next, we apply this contraction mapping on U, so U goes to U, and obtain the solution to these equations for U and V. This was originally proposed by Goberg. And then we plug these U and V into these formula down here to get expressions for the three parameters of the inverse, R0, R1, and R2. And of course, the question is, right, do these contractions converge? And in fact, actually, they have very good convergence properties that converge as 1 over k factorial, which is about as good as you want to get. So now we have a framework for representing infinite dimensional systems, representing Lyapunov functions for those systems, representing their derivatives, a test for positivity, and an ability to invert. And the question is, do we have a software tool which allows us to do all these things? And the answer is, of course, if I'm asking it, yes. So we have a software tool called PIETOOLS with a website and user manual and video and all this. And I'll go through this one real quickly because I'm running out of time. So what does PIETOOLS do? It basically creates an operator class within MATLAB, which allows you to manipulate pi operators in the same way you can matrices. So if A and B are op bars, then A star B will be an op bar as well. You can also combine multiplier matrices and operators. And it has formulas for all these things you do with matrices and probably don't think about. So how do we going to use this to do optimal control? So first, of course, we found over the years that the hardest part of using the software is actually getting your model in there in the first place. So for that, we have two options. The first is a command line interface where you declare your variables and states as these states, right, in and out. And then you can just declare your PDE using standard commands like addition, differentiation, subtraction, and integration to create equations, which then you can then add using add equation to a system structure in the same way that YALMIP allows you to add constraints. So you build up a PDE in this way, and don't forget your boundary conditions, of course. Alternatively, if you like to visualize things as you go, there's a graphical user interface which allows you to see the PDE as you're constructing it. Finally, for DDEs, I've got to admit, this was my job. I should have integrated this with the other interfaces, but right, for DDEs, you have to declare the actual parameters that you need from this general structure. So hopefully we'll integrate DDEs into the command line and graphical interface at some point. Given your model as a PDE or DDE, the next step is a conversion, of course, right? So we have this hierarchy in models. DDE is the lowest, pi is the highest, and ODE, PDE is there in the middle. And so the most important conversion routine is to take that PDE structure and convert it to a pi, which then outputs a pi data structure. Right? And what does that pi data structure look like? Well, it looks like these several parameters in the pi model. And these are all output to the workspace as opvars, meaning you can manipulate them as pi operators, right? The same way you can matrices. They're output as opvars to the workspace. So now how are you going to optimize using those opvars? And so now we have a tool for optimization of pi operators. So as with any optimization problem, there's three parts. First, you declare decision variables. In this case, we're doing optimal control, so those are P and Z. Next, you add your constraints, P greater than 0, D less than 0. And finally, you declare an objective function. So how do you do those three parts? First, you initialize the program. By the way, this is built on top. This is a meta parser. It's built on top of SOS tools. So it retains some of that SOS tools structure. You declare a decision variable using this var command, pos lpi var, which outputs an op var in the workspace, which is constrained to be positive. If you don't want it to be positive, then don't add the pos part. It's just lpi var. Next, you add equality and inequality constraints. This constrains P here to be equal to 0. Right? That's an equality constraint. And this constrains P to be greater than or equal to 0, whatever P happens to be. It's some op var in the workspace. Next, you set your objective function, which is a scalar in the decision variables. You solve the problem using, again, functionality from SOS tools, SOS solve. And then the output is the solution to your optimization problem. So just to illustrate the work through, the key commands here are, right, you initialize your program structure. You didn't have to pass that back and forth every time. We're adding a decision variable here, gamma. We declare our positive LPI var P. We declare our indefinite LPI var Z. And then we construct that big matrix from the controller synthesis condition, right? And we do this, right, just by composing these operators together, concatenating them together, whatever you used to do with matrices, you can do with opvars. Then we constrain it to be negative by constraining the negative to be positive. Right? We set our objective as gamma. We solve the problem. We obtain the solution using getSol. And these are opvars themselves. And then we can invert P and multiply it by Z in order to get the controller gains. So what do you do with the controller gains? Of course, the obvious thing to do is to simulate them and see if they actually work. And for that, we have PySim, which is included in PIETOOLS as a simulation toolbox, which will simulate PDEs, PIs, or DDEs, right? Sort of a universal toolbox for simulation. And the input is the PDE and some options, and the output is the solution, which you can then plot. And here's just an illustration of that. For a time delay systems, this is the open loop stable, the unstable we simulated. We close the loop and it rejects disturbances quite efficiently. So to conclude, right, the key elements that I wanted to emphasize in this talk are the existence of this partial integral algebra, which allows us to parameterize the dynamics of PDEs, parameterize Lyapunov functions on those states, parameterize the derivative of those Lyapunov functions, and the existence of efficient tools for optimization of such operators. Now, the existence of this algebra allows us to represent a very large unified class of infinite dimensional systems by eliminating boundary conditions and continuity constraints, yielding a unitary representation without constraint. This allows us to treat these operator parameters like matrices, leverage the intuition we have from state space systems for ODEs, and of course, simplifies simulation tools. Implemented in PIETOOLS, available online, both the model input conversion and optimization capabilities. And to conclude, I'll thank the audience for your attention.
Well, thanks very much for an interesting talk, Matthew. It's always interesting to hear about your research, and hopefully we'll have interesting questions. So feel free, audience, to open your mics, and then we can have a Q&A if there are any questions.
Yeah, I have a question.
Yeah, please.
So at least the two examples that you showed us at the beginning for the wave equation and the heat equation, you had a very specific choice of boundary conditions there, right? It was Dirichlet on the left and Neumann on the right.
Mm-hmm.
So my question is, does this approach work for any well-posed PDE, or are there any restrictions, and what kind of restrictions, if there are any?
Because the solutions are equivalent, if the original PDE is well posed, the pi will be well posed. These particular examples were chosen at the very beginning to like illustrate the process because they result in relatively simple PDE or pies. But the formulas work in general for any. So if the number of boundary conditions equals the number of partial derivatives in the state, then this works. The one thing we're still working on is periodic boundary conditions, because those things are a bit dodgy. We have a result, but it didn't work out very well. So we're still fussing with that one. But generally, yeah, it's not specific. You formulate your boundary conditions in sort of this general form defined by a B matrix. So this should generally be, for this system, 2 rows, so 2 constraints. And then when we get down here, way down here, right? This B multiplies by this T, and then you invert it, and that's the key step. So again, there are papers which address the class of inadmissible boundary conditions, but generally speaking, if the PDE is well posed, then the pi will exist.
And can you manage with the exponential stability? Because for the usual stability, it's enough to require that V dot is less equal than 0. But for the exponential stability, you need to upper bound it with the like minus alpha V. And then here it appears as if you like forget about your initial state without the derivatives, right? So the upper bound, at least in the example that you showed, it was actually in terms of the second order derivative, if I remember correctly.
Yes, so it depends on what precisely you want. So there's 2 versions of this, right? So this is V dot, right? So the V is here T P star P X. And then the derivative is this. So you can either constrain this to be less than epsilon alpha I, or constrain it to be less than alpha T star T, right? So if it's less than T star T, you get exponential stability in Tx, right? If you just make it less than alpha I, you get something slightly different. So there's, so remember V is, this is V, which is equal, so this is the fundamental state, right? And so this is the primal PDE state. And so V is equal to, in the PDE state. And then if it's less than 0, right, this is, so this becomes the PDE state again. So if you want exponential in the PDE state, right, then you add a little T star T term to the right-hand side. But we often don't bother.
Thank you.
Any other questions for the speaker at this time? Actually, I had one question about the delay part, and in particular, whether you can handle time-varying delays, and if so, what conditions you may need on the time-varying part of the delay, and also whether you can have uncertainties in your delays.
So time varying delays are problematic because if we think about the PDE representation of such a system right here, think about the PDE representation of a system, of a time delay system, we think of a pipe, right? You've got something going in one end and coming out the other. If you have time varying delay, essentially your pipe is contracting and expanding over time, which creates potential issues with well-posedness, and certainly would cause problems with a pi representation thereof. So you can imagine that if your pipe is is expanding faster than time is flowing through it, right? You have like a gap in your pipe, which like an air gap or something, like collapse or something like that. But that creates issues with well-posedness. So for time varying delay, we don't have a good pi representation of that. Now we can do quadratic stability, right? So you find, right, so this is a function of tau, the delay here. So you've proved stability for one value of tau, and you prove stability for another value of tau, where those are the endpoints of this, right, a tau, you call it. And you use a common Lyapunov function for both of those points, right? It will, by the convexity, it will give you a Lyapunov function, which is good for all points in between. So you can get quadratic stability results for these systems. Actually, we have a recent result using IQCs, which adds some multipliers to that and improves the accuracy of the quadratic stability criterion. Yeah, but time varying delays, no, and not state varying delays, because of course they're not linear.
Okay, well, any other questions for the speaker at this time?
So I have one final question.
Yeah, please.
Yeah, so for your software, when you solve, you call SOS solve. So for that, what software do you call? Or you make your own solver for solving the SOS problem or the SDP? So that's kind of yeah.
Yeah. Okay. Yeah. So this is actually a SOS tools function, right? So I'm also an author on, we're also authors on SOS tools. So the SOS solve is from SOS tools 4.0, and what
so what
our algorithm is doing is like this is the same prog structure that SOS tools uses, and we are converting these operator inequalities, right? P equals Z star Q Z to LMI constraints, and for every time we add a constraint, we convert that to an LMI constraint and add it into the prog structure. So essentially, we are an interface between these operator inequalities and the LMI conditions inside prog. So we don't use much of SOS tools other than its solver and its data structures. But
okay, you do call the solver to solve the SOS.
Yeah.
Yeah. Okay.
There aren't actually any SOS constraints in the.
Yeah, there are SOS. Yeah.
They're actually not SOS constraints. So SOS constraints are typically like K of S comma theta greater than or equal to 0.
Yeah. Okay.
Yeah. I mean, yeah.
Okay.
Well, actually, implicitly there is an SOS constraint in here for positivity. Yeah. So the multiplier actually is SOS. So I take that back. There is an SOS constraint.
Yeah.
We fuss more with the kernels than the multipliers because, right?
So I wonder. So for when you translate to this problems, normally the SDP or SOS they cannot solve a large dimensional problem. So here, what is the problem side of your problem?
Yeah, well, fortunately for us, our independent variables are scalars, right? Although I think Declan has a 2D case, but because they're scalars, right, the vector of monomials is just 1s squared s to the 10th, right? So the matrices here are not big. So we can solve, say, on a good day, 50 coupled PDEs.
Okay, so I'm good now.
All right, any other questions for the speaker? Okay, well, if not, then let's again thank Matthew for a very interesting talk. We have no control seminar next week due to the holiday break at LSU, but in 2 weeks, we will have our next LSU Zoom control and optimization seminar at the same 9:30 a.m. Central Time meeting time.